Chastity Reed. Peter Postma of FilmLight gave an incredible presentation at the May 2009 LA Red Users Group gathering. His talk on color management was quite an eye-opener.
So a spectrometer is much more powerful, but it's also much more expensive. What it does is it measures the complete spectrum of light, gets a complete picture of the display, what that display is doing for reproducing color, and from that can then, it will work with any display device because it is measuring the whole spectrum of what's happening. The problems with it, besides the price, are that it can be very slow to take measurements. Because it's basically chopping up the light into tiny little slivers, it needs to do a long exposure to collect all the data, and it can take up to 2 minutes just to do one reading, where you get it in a fraction of a second from a tricolorimeter. But what you'll get is a graph that looks like this. So that's what a CRT's phosphors looks like. That's what a fluorescent backlit LCD looks like. Even though these two graphs are very different, again, they're both just trying to get red, green, and blue light to the 3 receptors in our eye. So using a little bit of color science know-how, knowing how the eye sees light, we can make these two display devices reproduce very similar colors.
Someone said you can't use the same test charts that you've always used for CRTs to set up an LCD?
Well, the problem is that, yeah, the color gamut is slightly different. So you may have colors on your test chart that are within the gamut of a CRT, but not within an LCD. So they're effectively getting clipped in the LCD. And once they're clipped, they could be clipped more saturated, they could be clipped darker. You don't know which direction they're being pushed, essentially. So that's why, yeah, you really want to be able to measure the display device and get some numbers so you know what it's doing rather than just going off a chart. Although, as soon as I say that, you can't completely trust your probes either, because we have all these great mathematical models and all these great tools that emulate exactly how our eye sees light. Unfortunately, you have this pesky thing called the brain, which processes these images and does some other stuff to help us see the world better, but we don't have a good way of mathematically modeling it. So I have a test image here, which is a little bit off color balance. There's a cyan filter over the whole image. But you see the woman holding a raft. What color is the raft she's holding?
Yellow.
Yellow. Yeah, clearly it's yellow. And if I remove that cyan filter, you can see, yeah, it's still yellow. Now, if I take that cyan filter and put it just on the raft, all of a sudden that raft looks lime green. If I toggle between the images here, you'll see I'm not changing the color of the raft, but in this image it looks green, and in this image it looks yellow. And that's because your eye is comparing the color of the raft to the colors around it. It's always looking at the image as a whole and comparing colors within the image. So here it's kind of doing a white balance to normal and saying, well, hey, that thing looks really green. Here it's compensating for the color cast of the image and saying, oh, well, that's a normal yellow. And even when you see it side by side like this, the effect is the same. And the problem is if I take a probe and measure this and take a probe and measure this, it'll tell me they're exactly the same thing, that I'm getting exactly the same numbers. The same number of photons and same spectrum is hitting my eye, but our brain perceives it differently. And that's important not only within the context of an image, but also in your viewing environment. If you're looking at a monitor, under a set with lights or outdoors or something like that, you're going to have a very different color perception than if you viewed that monitor in a dark room. So if you want to try to match, get to see on set what something is going to look like in a color grading theater, that's why you need the tent and everything else. And oh, by the way, it takes some time for your eye to adapt from one to another. So if you really want to try to nail it as exact as possible, you have to actually sit in that room for a while, let your eyes adapt as they would in a color correction suite, so that all that is taken into account. And the same thing works even for smaller differences, like just for tungsten versus daylight color balanced. On the left here, I have a daylight image that's with tungsten balanced film. And then if I put that effect just on the raft, this raft suddenly looks way more washed out than it does if I've done the tungsten balance across the whole image. Here's another image with a checkerboard pattern, and obviously the square marked B here is much brighter than the square marked A, except that they're actually the exact same brightness value. Again, a probe would measure these as exactly the same. We see them as same when I break the illusion here, but what's happening is that the B is in shadow, so we say, well, it must be brighter because it's in shadow, whereas the A squared is outside the shadow within the light, so it must be darker, but in fact they're exactly the same. And this happens even with color. If I have a color that's in shadow, it will look brighter than a color that's not in shadow, even though physically the exact same light is coming out of this monitor. And again, if I break the illusion to kind of get outside the shadow, we see that it's obviously both those dots are the same color. So you can probably guess by now what's going to happen with this image. I have a gray square and I have a white square, but in fact it's actually the same color gray in the center of both of those squares because of our way of processing the image and trying to make these into real-world objects. Here's another image with 2 color patches of the exact same luminance, exact same color on the left-hand side and right-hand side of the image. It's the same brightness on both. You will probably see the left image as darker than the right image. And if I just block out what's going on in the middle there, you'll clearly see that they're the same. So if I just toggle that on and off, I'm not changing the luminance outside of the middle there at all, but you'll see the left as darker than the right. And what's going on here is that I put a little ramp in there. So I'm dipping down in luminance, then jumping up and going back to the same luminance level. But our brain has a sharpening filter in it that basically exaggerates edges, helps us see objects better, and this little ramp is getting amplified by the sharpening filter in our brain, so we see the left side is darker than the right side, even though they're exactly the same. And this is important to keep in mind when you're in a DI suite, because kind of the ultimate test for is my color management working is putting film projection and digital projection side by side and making sure they match. But what will often happen is you'll get a little color fringing in the middle when you put up a butterfly projection like this, and one side may go a little blue and one side may go a little yellow. And if you just look at the image like this, you'll see this image is a little bit cooler than the image on the right. And if I block that out, you'll see they're actually the same color values. So when you're looking at a projection like that, you have to put your finger up or put a pencil up or just block out what's going on in the middle so that you make sure you're looking at the image and not being affected by any either luminance or color fringing that's happening in the middle there. Here's another test image. If you could just focus your eyes on the black dot at the center of the screen and try not to move your eyes or head for a second. I'm going to change the image. And now you can move your eyes. And you should see it go from a color to a black and white image, even though I'm not changing it. So again, keep focused on the center of the image. Focus on that black dot for a second. Don't move your eyes. And then move your eyes. So what's happening is that your brain is basically getting fatigued by these bright colors. It's dialing them back and applying that to this image. As soon as you move your eyes, it kind of clears the buffer and says, whoa, that's actually a black and white image. But this is important in color correction when you're color correcting a scene that's really moody. Say you're going for like a really dark, really blue look. The longer you spend color correcting that scene, the bluer and the moodier you'll keep pushing it because it starts looking more and more normal to you. So a good colorist will constantly toggle back to either the uncorrected scene just to see how far you've gone, or toggle back to an image earlier in the sequence or later in the sequence, just to make sure that things are staying the same and you're not getting kind of lost in the look and it's not suddenly feeling less intense than you wanted it to, because when you watch it all cut together, that sequence may be a minute or two long and the audience doesn't adapt to it as much as when you're spending an hour or two color grading it. So you just have to be aware that your eye does kind of automatically try to balance and get you back to normal and basically dial back on these looks. To get back to the practical side for a minute of actually making 2 display devices match each other, there's a lot of talk about making sure the gamma curves match, and that is important. The gamma curve, again, is how it transitions from black to white. And it's a gamma function because mathematically it can be represented by a power function. So a digital projector has a 2.6 gamma. CRT might have a 2.4 or 2.5 gamma. If I just create a little lookup table to adjust for those, I can make them match. Except actually the biggest difference is that a digital projector is only getting up to 15-foot Lamberts and a CRT is going up to 30-foot Lamberts. So if I put them side by side in the same room, the CRT will look much brighter than the digital projector. But if I take the CRT and put it under office lighting conditions and leave the digital projector in a totally black room, they'll look more or less the same because our eyes adapt to our natural environment. The CRT needs to be brighter to appear the same brightness as a digital projector in a totally dark theater.
The LA Red Users Group meets monthly at Kappa Studios in Burbank. From Hollywood, I'm Chastity Reed.